Good day, students. Let us begin our revision by looking at how decisions differ across strategic, operational, and control levels. To make this clearer, we will use the Cybertruck launch by Tesla. This example shows how product, process, and service design come together in a real business setting. At the strategic level, Tesla must think long-term. This is where the company decides on the Cybertruck's entire design philosophy. You may recall its unique steel exterior, its electric drivetrain, and its autonomous driving capability. These are not small tweaks. They are core design choices that shape brand identity for years. They must reflect Tesla's wider commitment to sustainability and innovation. As we move to operational decisions, the focus shifts to day-to-day practicality. Tesla needs to adjust its factories, especially the gigafactories, to fit the Cybertruck's unusual structure. This includes reorganizing assembly lines, adding specialized automation, and working with suppliers who can provide the unusual materials. These decisions happen more frequently and must align with production schedules. Control decisions, however, sit at the shortest time frame. Here, Tesla monitors outputs in real time. Managers look at defect rates, takt time, and whether the process stays within specification. When something goes off target, immediate action is taken. Control decisions protect consistency. Strategic thinking also shapes Tesla's service design. The company must create a long-term after-sales ecosystem. This includes a global network of service centers, mobile repair units, and over-the-air diagnostics. These choices support brand loyalty and customer trust. Operationally, Tesla must ensure that technicians are properly trained to handle the Cybertruck's non-traditional materials. Technicians who understand the product well can deliver better service, which improves customer experience. Finally, Tesla uses control-level decisions to study customer feedback. Through the Tesla app, patterns and complaints can be identified quickly. These insights guide corrective actions. Now that you see how Tesla connects the three levels of decision-making, let us move forward to another global giant dealing with capacity and layout decisions. Now let us shift from automobiles to logistics. Amazon's new fulfillment center in Johor offers a strong example of how capacity planning and layout decisions differ across decision levels. The ideas build on what we just discussed, but now applied to warehouse operations. Strategically, Amazon must forecast long-term regional demand. This shapes the overall capacity of the Johor facility. It determines the size of the land required, the level of automation, and the investment needed. These decisions support future growth and ensure that the facility will not become obsolete. At the operational level, Amazon focuses on resource allocation. Managers must decide on labor shifts, machine hours, and how many material handling devices are needed to maintain throughput. These decisions allow the fulfillment center to meet daily order requirements. At the control level, Amazon examines real-time data. Dashboards show utilization rates, congestion points, and backlogs. When an area becomes overloaded, staff can be reassigned or packages rerouted. Control decisions allow fast responses. Strategically, Amazon must also choose the right layout. Different layouts such as cross-docking or U-flow influence how quickly goods move through the warehouse. These choices align with Amazon's promise of fast delivery. Operational layout decisions involve zoning and organizing workstations. This ensures smooth flow between receiving, sorting, and packing. It reduces unnecessary motion and prevents fatigue. Finally, Amazon uses control-level monitoring to detect bottlenecks. When a zone becomes slow, temporary layout changes can be made. Now that we have seen Amazon's approach, let us turn to Toyota and explore how quality decisions operate at different levels within a manufacturing environment. Let us now discuss how AirAsia evaluates the location for its new maintenance, repair, and overhaul hub in East Malaysia. Location decisions influence cost, compliance, and operational performance. Strategically, AirAsia must ask whether the facility supports its long-term regional plans. A hub in East Malaysia may strengthen connections to Borneo and surrounding regions. It could reduce turnaround time and improve cost efficiency. Operational decisions include evaluating the site's proximity to key airports and suppliers. Daily operations depend on reliable access to aviation-grade materials, airside facilities, and smooth logistics routes. Control decisions involve checking compliance with regulations. The Civil Aviation Authority of Malaysia and IATA impose strict standards. Regular audits ensure that procedures meet safety expectations. Failure to comply can result in penalties. Strategically, AirAsia must also evaluate labor availability. An MRO requires skilled engineers and technicians. This may involve partnerships with aviation training institutes. The long-term sustainability of the hub depends on a strong talent pipeline. Operational decisions include analyzing roads, electricity, water supply, and communication infrastructure. These utilities affect the layout and efficiency of the facility. Control decisions include monitoring the hub's performance. Key indicators such as turnaround time, cost per maintenance event, and safety metrics guide adjustments. This brings us to our final section, where we shift from aviation to semiconductor manufacturing. Let us examine how Intel uses planning and scheduling decisions to achieve continuous production. Let us continue by looking at Toyota's manufacturing plant in Shah Alam. The company is addressing interior quality issues. This situation helps us understand how quality decisions interact at strategic, operational, and control levels. Strategically, Toyota must reaffirm its commitment to total quality management. This is a long-term philosophy. It requires quality to be embedded in the mission, in leadership behavior, and across the supply chain. Without this strategic direction, operational efforts would lack coherence. Operationally, Toyota must strengthen supplier coordination. Interior components come from external parties. Therefore, suppliers must meet strict quality standards. This means frequent evaluations, training programs, and synchronized delivery schedules. Operational decisions ensure materials entering the system are reliable. At the control level, Toyota performs layered process audits. These audits check each workstation step by step. They help identify deviations quickly. When an issue is detected early, defects do not move downstream. Strategic decisions also include actions that uphold customer assurance. Toyota might extend warranties or communicate openly with customers to maintain trust. This reinforces loyalty. Operational decisions further involve the use of analytic tools such as fishbone diagrams and Pareto charts. These help teams identify root causes and prioritize improvement areas. Control decisions include monitoring statistical process control charts. These charts detect variation and signal when immediate intervention is required. Now that we have explored Toyota's approach, let us move into a different setting. The next section examines location decisions in the aviation industry, using AirAsia as the focal example. Before we move on to our final revision section, please do not forget to like this video, subscribe and comment. Now let us focus on Intel's manufacturing plant in Penang. The company faces rising global demand for chips. This requires a planning and scheduling strategy that integrates strategic, operational, and controlled decisions. Strategically, Intel must forecast global chip demand. These forecasts shape the master production schedule. They ensure long-term alignment between production capacity, supply chain capability, and market needs. Operationally, Intel relies on material requirement planning. The system determines what materials must be ordered, when they should arrive, and in what quantities. Semiconductor production requires silicon wafers, rare earth elements, and cleanroom supplies. Operational planning ensures efficiency without excessive inventory. Control scheduling decisions involve real-time monitoring. Manufacturing execution systems track work orders as they move through the plant. When delays occur, managers can adjust the schedule to prevent bottlenecks. Strategically, Intel must also collaborate with suppliers. The company may reserve capacity in advance to avoid shortages during global supply disruptions. These agreements protect long-term production stability. Operational decisions include workforce shift planning. Semiconductor fabrication runs around the clock. Skilled labor must be available at all times. This reduces downtime and maintains momentum. Finally, control decisions rely on performance metrics. Intel monitors overall equipment effectiveness and cycle time. These metrics show whether machines are performing as expected. When performance drops, immediate action is taken.